Hi, my name is Nick Braun, and I'm a researcher at IBM Quantum. Today, I'm thrilled to host the first of a two-part series that explores all of the Qiskit applications modules. I don't know about you, but today I'm calling in from Heidelberg, Germany. Why don't you let us know where you're watching from? Drop it in the chat while we get started. Bonus points for anyone watching from the location of today's speakers. And speaking of the chat, that's where you can ask questions to any of our speakers, where I'll be monitoring it so I can interrupt or bring it to the attention of our speakers when they conclude. So while we get started, let's see where people are calling from. Oh, wow, we've got Taiwan, Indonesia, India, Brazil, Mexico, Tokyo, Japan. You don't count, Yuri. I know you. Brazil again. Another Tokyo. Okay, so Tokyo is one of our speakers today. That's great. We've got Czech Republic, Turkey, Singapore, Nepal, Morocco. Quite a bunch today. Italy, Japan, and I thought I was in the messed up time zone. Chile. Oh, this is really good. Did I say Mexico? Wonderful. Okay, Tanzania. Great. Bolivia. Great. Really nice to hear from such a diverse group of geographies. Thailand, Korea, Bogota. Wow, I keep going. Okay, well, I don't want to cut into the speaker's time today because we have a lot of interesting things to learn. So I'm going to go ahead and give my introductions. And the first speaker I'd like to introduce is calling in from Tokyo, Japan. With the title, The Introduction to Qiskit Optimization, is Atsushi Matsuo, who is a researcher at IBM Research Tokyo. He received his master's degree in information science and engineering from Ritsumeikan University in 2013. His research interests include quantum circuit synthesis, compilers for quantum circuits, and quantum algorithms for current noisy devices, such as variational quantum algorithms. He is working on developing Qiskit, especially Qiskit optimization. Why don't you take it away for us, Atsushi?
Okay, so thank you very much, Nick. Okay, so let's get started. So today I will introduce Qiskit optimization. So this is today's agenda. So first, I will talk what optimization problems are. Then I will introduce Qiskit optimization. After that, I will show example of solving a max-cut problem with Qiskit optimization. And so most of you might not know about optimization problems, but many practical problems in several fields are optimization problems. So optimization problems lie at the core of complex decision making and definition of strategies. So optimization problems mean searching for an optimal solution in a finite or countably infinite set of potential solutions. And its optimality is defined with respect to some criterion function called objective function, which is to be minimized or maximized. And so these are typical objective function. So for example, for minimization, so we have cost, distance, or weight, or energy consumption like this. And for example, finding the shortest path from A to B is so one of the optimization problems based on minimizing distance. And so for maximization, so for example, we have profit, value, or so efficiency, like that. And so for example, so production planning, so we have limited machines and limited materials and schedule, and we want to make a product as much as we can. So yeah, these are typical objective functions. And so I hope you can get some idea. So what we want to solve with these optimization problems. And Qiskit optimization covered the whole range of solving optimization problems. So from high-level modeling of optimization problems, and so this is like a middleware automatic conversion of problems to required representation called Eigen Hamiltonians. And so it also, of course, include allows user to solve problems using a large set of algorithms such as QAOA, Global Adaptive Search, and classical solvers. And so this is the image of structure of Qiskit optimization. So at the high level, so we have the modeling part. So we can make a model of optimization problem. And we have lots of algorithms to solve that problem. And of course, it can connect to real quantum hardware. And so before going to explain Qiskit optimization deeply, so let me explain quadratic program first. So Qiskit optimization supports quadratically constrained quadratic program, including binary, integer, and continuous variables. And it also includes equality and inequality constraints. So formal representation will look like this, but it's so maybe complicated. So let's see a simple example. So this is a simple example of quadratic program. So we want to maximize 2xy plus x plus y plus z. So this is a objective function we want to maximize. And we have these constraints. So x, y, and z are binary variable, so which can be only 0 or 1. And we have this constraint, so x plus y plus z must be equal or less than 2. And so we need to find the optimal solution that satisfies this constraint. And so this example looks simple, but actually quadratic program covers various types of problems. For example, traveling salesman problem, TSP, max cut, vertex cover, knapsack problem, and so on. So it can cover lots of famous problems. And Qiskit optimization introduced a special class for quadratic programs. So the name is just a quadratic program class, and we can use this class to make a model of optimization problem. And so when modeling optimization problem, so there are 3 ways to make that. So first one is, so we can directly construct a quadratic program in Qiskit optimization. And second one is, so we can load quadratic program from other classical optimization library, like a DOCplex or GloBPy. Or so we can load a quadratic program from LP file. So LP file is a common file format for optimization problem. So, and not only constructing quadratic program in Qiskit optimization, so we can load from other file or other library as well. And so this is an example of constructing a quadratic program in Qiskit optimization. So first, we import quadratic program. Then, we define it. And after that, we add variables. And so in this example, we add variable x, y, and they are binary variable. And we also add variable z. So this is a integer variable. So which can be any integer from 0 to 7. And we add an objective function like this. So this means we want to maximize. So this is a 2x plus y plus z. So like this, we want to maximize this objective function. And so we can add a constraint as well, like this. So this constraint means x plus y plus z must be equal or less than 2. And so by writing the code like this, so we can make a model of optimization problem. This one. And after making a quadratic program, so quadratic program class is generic and powerful representation for optimization problems. So, but quantum algorithms cannot handle quadratic program directly. So we need to convert problems into quadratic unconstrained binary optimization, so QUBO programs. And after that, so we want to convert it to Eigen Hamiltonian, which quantum computer can understand. So this is the original problem model. So we first convert this original one to QUBO, so which is quadratic program, but it doesn't have constraints. And after that, so we map this QUBO to Eigen Hamiltonian, so which is a weighted sum of Pauli Z operator. Then we can solve this Eigen Hamiltonian by using quantum computer. So this task is very difficult and time consuming. So Qiskit offers a variety of converters, and it automatically converts problem to Eigen Hamiltonian. So users do not need to bother with this complicated conversion process. And so after converting problems into Eigen Hamiltonian, so we want to solve the problem. And to do that, so we want to find the minimum ground state, so minimum eigenvalue and minimum eigenvector of the Eigen Hamiltonian, because it's directly corresponding to the solution of original problem. And so for that purpose, so Qiskit offers a class called minimum eigen optimizer. And we can choose a variety of solving methods in minimum eigen optimizer, such as QAOA, VQE, or shapeless solvers. So this is a classical solver, and we can also use classical solver in minimum eigen optimizer. And also, Qiskit offers application classes for several optimization problems. So these application classes are predefined classes for specific problems. For example, max cut problem and traveling salesman problem, or exact cover problem, knapsack problem, and so on. So there are several predefined classes for specific problems. And by using these application classes, so users can easily make various optimization programs and try to solve them with quantum computers. And now, let's see an example of solving a max cut problem with QAOA using Qiskit optimization. So first, so max cut problem is so NP complete problem, and so it's known as so classically intractable problem. So it's a very difficult problem, and its applications are so for example clustering or network science and statistical physics and so on. So there are several applications for that problem. And formal definition of the problem is like this. So, but it's so difficult to understand at first. So let's see example first. So max cut problem is some graph problem. And so let's consider, so we have this graph. So 5 nodes and 6 edges. And yeah, let's ignore these colors first. And so what we want to do is, so we want to divide these nodes into 2 subsets. Then we want to maximize the number of edges connecting nodes in the 2 different subsets. And so in this example, so we have 5 nodes, right? And if we divide nodes into so this black and white subsets, and then so we can maximize the number of edges between so these black and white subsets. So yeah, let's count the number of edges. So this edge is between 2 different subsets, right? So 1, 2, 3, 4, 5. So yeah, we have 5 edges. And so this solution is the optimal one. So max cut is a problem like this. So divide nodes into 2 subsets, divide nodes into 2 subsets, and maximize the number of edge between 2 different subsets. And so yeah, let's use application class for max cut problem in Qiskit optimization. So first, so we use network X. So this is a Python library for graph. And we can also use this network X for application class of max cut. So first, so we make a random regular graph with the degree is 2 and the number of nodes is 5. So then we can make this graph like a pentagon. And so after making a graph, so we import max cut application class like this. Then we pass the graph to the constructor of max cut class. So then after passing the graph to the constructor, so we can make a quadratic program by simply calling this method. So to quadratic program method. Then so this max cut application class automatically makes quadratic program from that graph. So this formulation comes from that graph. And so after we got the quadratic program, so yeah, let's solve it with QAOA in this case. So to use QAOA, so we have several imports, and so define minimum Eigen optimizer, and we specify the solver is QAOA. And after that, so we simply pass so this MEO.solve function. So this, so we pass QP to this solve function. And so in this solve function, so the original quadratic programs are automatically converted into Eigen Hamiltonian, and it will be solved with it will be solved by QAOA. And the answer is like this. So optimal function value, so it's an objective function. The value is 4. And so which means, so we divide these nodes, these 5 nodes, into 2 subsets, like these blue and red subsets. Then, so the number of edges between 2 different subsets are, so yeah, we can count, so 1, 2, 3, 4, right? And it's so yeah, it's maximized. And so this MaxCut application class, so also has interpret, has a function called interpret. So the result is actually so binary, so bit strings like this. The result from QAOA. So but it's difficult to understand for humans. So we have interpret function, and interpret function maps so this binary string to like this. So this list tells us, so if we divide nodes into like this, so for red group, so we assign 0, 3, 4, and for blue group, we assign 1, 2, then this is the solution. So yeah, so by using application class, so we can also understand the solution easily. And this one was, so in this one, so we used QAOA to solve the problem. And so let's try with so NumPy eigensolver. So this is the classical optimizer to confirm the solution is correct or not. And so to use NumPy eigensolver, so it's similar to the QAOA case. So we define minimum eigenoptimizer and specify the solver. So in this case, so we write NumPy minimum eigensolver here. Then we pass quadratic program to solve function, and we can get result. So result is, so the objective function is 4. So, but the assignment is looks a little bit different, because in this program, so we have several optimal solutions. But yeah, their objective functions are the same, so they are all optimal. So if we divide nodes into like this, so nodes 0, 4 are in red group, and node 1, 2, 3 are in blue group. And we can also get the maximize the number of edge between 2 different groups. So 1, 2, 3, 4, right? So yeah, so we can use classical optimizer to check the answer from quantum computer as well. So yeah, this is the summary. So as I explained, so optimization problems lie at the core of complex decision making and definition of strategies. And so it's used to minimize cost, weight, or maximize profit, efficiency, and so on. And Qiskit optimization covers the whole range of solving optimization problems. So from high-level modeling to automatic conversion, and so it also contains predefined application classes to create problem easily. And yeah, of course, so we can solve the problem using a large set of algorithms, so QAOA or global adaptive search, or yeah, even classical solvers. And yeah, finally, I showed example of solving a max cut problem using Qiskit optimization. So in this example, so I used application class of max cut to create a problem, and so we solved that problem with QAOA and NumPy eigensolver. And so yeah, so this is it. And yeah, thank you for listening. So if you have any questions.
Yes, thank you so much for that summary of how to use Qiskit optimization to solve an important class of problems. In the meantime, I have some questions already for you, Atsushi. But if you have any further, please drop them in the chat and I'll get to them as soon as I can. The first question was from Narendra, asking, does Qiskit optimization only support kubo problems? How about higher order unconstrained binary optimization problems, or hubos? And we were discussing, we both think that should be possible, but wanted to get your opinion.
So currently, Qiskit optimization does not support higher order problem, but yeah, we are thinking, and we are planning to support like a higher order, like a third or fourth. Yeah.
Great. So that brings me to a question that me and another person had. So I saw you had a mapping from a quadratic program to a kubo to an Eigen Hamiltonian. And I am more familiar with Qiskit nature, which you can tune in next week for, where you have a bunch of different mappings that you can go from one class of problem to another class of problem. And I was wondering if you could elaborate on how many different ways you can do these mappings or conversions. And in particular, Adam asked, do you always need 1 qubit per node? Or what is the maximum number of nodes you can solve for given a set number of qubits?
So yeah, so for optimization problems, so we basically use only one mapping method. And in that mapping method, so we use 1 qubit for one variable. So for example, if if a problem contains like 100 variables, so we need 100 qubit.
Yeah, and that's always the case, unlike in some other kinds of like molecular simulations. Very interesting. Okay, do we have anything else in the chat? Oh, okay. Mafai is asking, do you only use VQE and QAOA for optimization?
Not really. So we have several algorithms for, in Qiskit optimization, and we can use anything you want.
Great, and you can find this all online on qiskit.org on the API documentation, and the tutorial is useful as well, I should say. I guess one last one real quick is Qiskit optimization flexible with choosing the mixer Hamiltonian, or does it always use the conventional transverse field as the mixer term?
So for mixing Hamiltonian, you mean?
For the mixer Hamiltonian, I believe.
For like a QAOA?
I believe so. That's where I've seen mixer Hamiltonians.
I see. Then we can choose different mixing Hamiltonian. So we can define. Just simply pass different Hamiltonian to the argument of QAOA.
All right, great. Well, thanks a lot for that talk, and thanks a lot for answering all of these questions. The ones I couldn't get to, I'll try and get to in the chat. And maybe you can log in as well, Atsushi, and assist. So for our next speaker, he's calling in from Dublin, Ireland, and he's going to be talking about an introduction to Qiskit machine learning. Anton Dekusar has been a research software engineer at IBM Research Dublin since 2017. His focus is in quantum algorithms and computing. He is an active contributor to Qiskit machine learning application module. Before joining the quantum team, he was working on software services for the transportation industry, mobility as a service, and application of machine learning and deep learning techniques for better quality of service. Prior to joining IBM Research, he held various positions in IBM Ireland and IBM Russia. Mr. Dekusar graduated from Moscow Engineering Physics Institute, Moscow, Russia. So I'm very interested to hear about this. Anton, please take it away.
Hello, everybody. Thank you, Nick, for introducing me. So yes, our next talk will be about Qiskit machine learning. And I prepared a few points I'm gonna talk about. So first of all, we will we'll have a brief introduction to Qiskit machine learning. This is our new module in the Qiskit application family. Then we will move to binary classification problem and support vector machines. Then, of course, we will take a look how quantum support vector machine look like and what's the difference with the classical implementation. And at the end of this talk, at this demo, we will take a look at the actual code, and we will train a quantum model that is based on quantum kernel. Okay, so first of all, let's take a look at the Qiskit machine learning packaging. So as I said, this is a brand new application module available in Qiskit application family. And here on the diagram, you see various components that are available in this module. So we start from bottom to top, and at the bottom we have Qiskit itself. And here we have circuits, library of circuits, we have operators, we have a gradient framework, and of course optimizers, because a lot of quantum algorithms, hybrid algorithms, they depend on optimizers. On the next level, we have neural networks and we have kernels. In neural networks, we have three types of networks. So first of all, Opflow QNN. So this network allows users to mix quantum circuits and quantum mechanical observables. And the output of such neural networks is an expectation value of these observable. So in this case, you may construct a network in a way that you pass two things. A special case of Opflow QNN is a two-layer QNN where you have to pass a feature map that actually loads your data into a quantum space, quantum world, and a trainable ansatz. The third type of quantum neural networks is a circuit QNN. In this case, we don't have a measurement operator. We just measure circuits directly, and we can translate or interpret the output of circuits into our domain. For example, if we get a bit string, we may translate or interpret a probability of such a bit string into a set of classes, and thus we can construct a classifier. On the right-hand side of this picture, we see kernels. We have just quantum kernel. We expect more to come here. And on top of quantum kernels, we have two algorithms. We have QSCC and QSVR, classifier and regressor. And as well as for kernels, we have a bunch of algorithms implemented on top of neural networks. Of course, we have very basic neural network classifier and neural network regressor. They take a neural network and then they can be trained, and then you can obtain results by calling a predict function. So same as in scikit-learn. Basically, the whole idea of Qiskit machine learning is to design a new package, a new module that would resemble scikit-learn available in Python. We want to have Qiskit machine learning as easy to use as possible. And for such purposes, we have additional classes, VQC and VQR. So variational quantum classifier and variational quantum regressor. And here you may pass just a feature map ansatz, or you may keep them as a default values, and you can train a quantum classifier. We will take a look how you can do that. All right, and on the top, we have a torch connector. So here you may wrap your neural network, your quantum neural network, as a layer, and you may plug in this layer into a classical neural network written in PyTorch. Once you plug it in your layer, you may train such a hybrid model where you have classical layers, where you have quantum layers, and you may get, of course, results you want. In this case, when we compute gradients, when we compute a backward pass of our neural networks, we rely on the gradient framework available in Qiskit. So yes, we have a lot of new computational blocks, and in this demo, we will focus mainly on quantum kernel and corresponding algorithms. Okay, let's move on and take a look at support vector machine and problem definition. We will talk about supervised binary classification. So suppose we were given a set of dots, red dots and blue dots. And these dots are in two-dimensional space. For example, we have a lot of pets, dogs and cats, and we want to distinguish them. But in our case, we are given only two measurements. For example, weights and tail lengths. And when we get a new measurement, when we get a new weight and tail length, we want to decide whether it is dog or cat. So this is our binary classification problem. We want to assign a label to such new data. So here on the picture, we have a training set T that consists of vectors in our feature space. And we have a map, predefined map, that maps all our dots into either +1 or -1, our classes. We also have a test set. It is not shown on this picture, but it is the same as a training set, but we don't know labels for these axes in the set. And our goal to find a map, in our case, this is C tilde, because we don't know the ideal map that would classify any sample. So our idea is to find this map that takes into account our training set and our test set. And this map should agree well with the unknown map C that determines all true labels. So how we can do that? And here we have support vector machine. Idea is to draw a line between two our classes. But there are many ways how you can do that. Idea here is to find support vectors or closest dots in red and blue to our line in a such way to maximize the distance between these two dotted lines on the picture. And the distance in this case is determined by 2 over norm of our vector W. So basically means that we want to minimize the norm of this vector if we want to maximize the margin between two classes. And here the problem definition, the math problem definition on the left-hand side. So we want to minimize the norm such that we take into account known labels of our training data set. That works perfectly well if we can draw a line between two classes. What if we cannot find a line, if we cannot draw such line between red and blue dots, in our case, cats and dogs? Okay, here we can introduce a nonlinear feature transformation. That means we want to map our samples from the original feature space into a higher dimensional feature space. And thus we can replace a a product of W and phi of X with the kernel. So we want to introduce a function that maps our data from initial original space to a high dimensional space. And idea here to have such a kernel and rewrite the SVM problem definition in a way that it depends explicitly only on kernel values. We don't want to compute our new feature vectors directly because it may be time consuming, resource consuming. We want to compute just kernel. And here is an example. Our original data was in R2, means that it is a two-dimensional data. And we want to map it into a R3 space. And in this case, we may choose a feature map phi of x in a way that it produces three values, x1, x2, x1 squared plus x2 squared. And our data in this case will be in a R3 space. And see here on the right-hand side that we can easily find a plane, in this case just an ordinary plane, that easily divides our dots into two classes. Of course, in real practice, you may have more dimensions, and your plane will be a real hyperplane in multi-dimensional space. Okay, that was pretty simple, and we are still in the classical world. Let's move on to quantum things. So we still have this optimization problem to solve, and we still solve it on a classical machine. You may ask why. Okay, we had a presentation where we discussed optimization. Why don't we want to solve this problem on a quantum computer? Well, so now we cannot do that easily because quantum computers, they are good for discrete optimization. But in our case, we deal with a continuous optimization, and we cannot easily, solve this problem, this optimization problem on a quantum computer. So we still have to solve our optimization problem on a classical computer, as I said. But instead of computing kernel on a classical computer, we want to compute it on a quantum machine. And here we introduce E of x as a feature map that maps our original data to a high dimensional space. And we can introduce a quantum kernel as a Hilbert-Schmidt inner product. That means we can easily compute our kernel by applying two feature maps. So first of all, we apply a feature map E of x, and thus we load our data from a classical representation to a quantum representation. And then we apply E of x prime conjugate transposed, and thus we can compute kernel. So this is pretty easy to implement on a quantum machine. And in this case, you may have different feature maps and different ways how you can load your data, your classical data, into a quantum representation. Okay, let's move on and take a look at the actual quantum kernel demo, how we can load this data into a quantum representation and how we can train our model. In our example, we will use an ad hoc data set as described in the paper Supervised Learning with Quantum Enhanced Feature Spaces. The paper was published by our colleagues from IBM Quantum, and you can find this paper on this link. We also will use scikit-learn where we have a quantum support vector implementation, quantum support vector machine implementation. This is a widely known, scikit-learn, a widely known in Python world library where you can find a lot of classical machine learning algorithms. And finally, we will take a look at QSVC. This is just a wrapper available in Qiskit Machine Learning for sake of simplicity, and you may use it just as a beginner. You don't have to know much about actual quantum computing. Okay, so first of all, we want to sample our train and test data sets. For such purposes, we have a special function provided in Qiskit machine learning. We import this function Adhoc Data. We fix the number of dimensions. In our case, we have 2 dimensions. And then we just call this function and we pass the number of training samples, the number of test samples. This will be our data sets. We pass a number of dimensions and a few additional parameters. So as an output, we get train features, train labels, test features, test labels, and ad hoc total. First, for variables, they represent our training and test dataset. The ad hoc total is only required to see how the dataset look like. So now let's plot the datasets. In this notebook, we have a special predefined function. It is not available in Qiskit machine learning. So this is just for our purposes. We plot this dataset, and you may see different areas in red and blue. If you recall, blue our dogs and red our cats. So any single point in a blue area is a dog, and same, any single point in red areas is a cat. So here you may see additional dots on this plot. Blank dots in blue and in red, they represent our training set, and solid dots sampled from blue areas and from red areas represent our training set. So let's move on and try to train a model that would try to classify our pets. So first of all, we have to define where we want to execute our quantum circuits. For that purposes, we create a quantum instance and we pass a Chasm Simulator instance to this quantum instance. Chasm Simulator is a noisy simulator, and that is why we would like to see quite a high number of shots to reduce this noise. Of course, instead of Chasm Simulator, you may pass a reference to the actual backend available on IBM Cloud, for example. And also, we want to fix seeds for the simulator and for the transpiler. We want to have reproducible results. Okay, once we have this quantum instance, we can instantiate a feature map. We'll start from a Z feature map. In this case, we pass a number of dimensions to the Z feature map, and we pass reps or repetitions as 2. We'll take a look what it means a little bit later. So here we have an instance of feature map, and we create a kernel, Z_kernel, that has 2 parameters, feature map itself and quantum instance where the circuits will be executed. All right, so let's take a look at the feature map itself. Actually, choice of a feature map is a key decision. You may get good results or you may get not so good results if you choose different feature maps. So as I said before, feature map is a way how to load your classical data into a quantum representation. And here we see how Z feature map looks like. Here we have 2 qubits noted as Q0 and Q1, and we have a few gates applied on these qubits. We have Hadamard gates, and then we have P gates or phase gates. And this is just a rotation around a z-axis. And as a parameter of these gates, we have references to our data, x0 and x1. So here we parameterize our feature map. And then we have, again, a Hadamard gate and the rotation gate. See that we have 2 blocks of identical gates. That is what repetition means here. We have 2 repetitions of the same block of gates. And you may notice that we don't have 2 qubit gates here, means that we don't have entanglement between qubits, and that means this feature map can be simulated quite easily on a classical computer. Okay, let's try to train a model. So we'll use, as I said, SVC algorithm from scikit-learn. And in this case, there are two ways how you can provide a custom kernel. First of all, you may provide the kernel as a callable function, or you may pre-compute your kernel and pass just the metrics. In this demo, we will use kernel as a callable function. In this case, we just import SVC from scikit-learn and we pass a kernel parameter as a z_kernel.evaluate. So kernel.evaluate, this is our callable, this is our function that evaluates our kernel values. So once we have an instance of SVC, the rest is pretty straightforward. You call svc.fit and you pass your training features, your training labels, and you get a trained model. Then you call svc.score just to get your score, how your model performs. You pass your test dataset, test features and test labels. In our case, we get a score of 0.6. Well, not so good, not so bad actually. At least it is better than tossing a fair coin, but we definitely have a room for improvement. We can improve our model. Okay, let's try then another feature map. We can take a look at ZZ feature map. Since this is another feature map, we have to recreate a kernel using this feature map. Let's take a look how it looks like. A picture is slightly different. Yeah, I forgot to mention that we still have the same parameters when we instantiate a Z feature map. We pass a number of dimensions, we pass repetitions, and here we have another parameter called entanglement. It explains how you entangle qubits in your feature map. Since we have just 2 qubits, it doesn't actually matter what you have in this parameter. But if you have more qubits, you should pay attention at this parameter. Okay, so we have 2 repetitions. So we expect to have 2 blocks, 2 identical blocks in our feature map. And yes, we can see that. We have Hadamard gates as it was with Z feature map. We still have rotations, same rotations, but then we have 2 C nodes and an additional rotation between them. And this additional rotation depends not only on one feature, it depends on 2 features. So here we have nonlinear data representation plus entanglement. So we may think that we may get better results. Let's try. So we'll train a classifier with the ZZ feature map. Same as it was before, we create an instance, we pass zz_kernel.evaluate, we fit a model, and we run a score. In this case, of course, we get a better score. A score of 1 means that we classified our test dataset absolutely correctly. Well, it's not a surprise because the dataset itself was designed in a way that ZZ feature map can easily classify this dataset. So this is pretty artificial dataset, specially designed to show that we may obtain some advantage here. Okay, now the easiest way how you can get your hands dirty with quantum computing and quantum machine learning is to use QSC Class. This class extends scikit-learn SVC and can be used pretty straightforward. So you import QSVC from Qiskit machine learning. This is not from scikit-learn. This is our class from our library. And the only one thing we want to do here is to assign a quantum instance and quantum kernel. So you do that by assigning your quantum instance on the 3rd line of the snippet. So after that, our instance of QSVC is ready for use. You do the same as in classical SVC. You just call .fit, you pass your training dataset, train features, train labels, and then you call score passing your test dataset. In this case, we get the same score. Well, it's because by default, QSVC uses this ZZ feature map is a way to represent your classical data in quantum world. So if you have other values, other samples you want to use for prediction, you may call just predict method. And in this case, you pass test features and you get an array of labels. In our case, these are just zeros and ones. So basically, this is the easiest way how you can train a quantum model, quantum classifier. All right, so that was a very brief introduction to Qiskit machine learning. I want also to let you know that we have more resources. So first of all, take a look at the blog post introducing Qiskit machine learning, and you may find more details about components in Qiskit machine learning. Also, we have a few tutorials available online. Please check out the link here and the reference to the paper Supervised Learning with Quantum Enhanced Feature Spaces. Thank you very much for listening, and let me know if you have any questions.
Thank you so much, Anton. That was a great introduction to quantum machine learning with Qiskit. We have several questions, and feel free to add more to the chat. But I'd like to start out with a question about the number of input features and number of qubits. Does it always scale linearly? Is it always one-to-one? Or are there ways to minimize the needed qubits for other purposes or with other purposes?
In our case, we map qubits one-to-one to features. So as many features you have, as many qubits are required to run these algorithms.
Well, are there other methods that are possible?
Well, perhaps not right now. You may try to build your own, say, algorithm, and in this case, you may get different results, of course.
Okay, great. There was another question, and it ties into one I had as well. It was Ahmed asked, how do repetitions affect the results? And similarly, I was thinking about the amount of entanglement, because it seems to me that when you map this to actual hardware, it will depend on the topology of the quantum hardware you're running on. For example, like on our current systems, linear might work better for small data sets due to limited swaps than over circular, but circular could work better on larger sets due to the heavy hex architecture for larger data sets.
Well, this is a very good question. So the algorithm itself it doesn't know about hardware topology. Means that the algorithm doesn't care what you have as a quantum computer. And of course, once you get a quantum kernel, once you want to execute circuits, you want to actually compute values of your kernel. Of course, you have to execute circuits. And then they have to be transpiled to take into account actual hardware limitations, topology or coupling map. And of course, in this case, if you want to be efficient, you should know your hardware topology. And of course, if you choose different entanglements, you may obtain different, say, circuits to be executed. But as I said, the algorithm itself doesn't know about hardware. It is hardware agnostic, and it is up to a user to define a feature map, entanglement, or if you want to have your own custom feature map, so feel free to create it. But of course, if you want to adhere certain limitations, it's up to a user.
Well, that's great, and I look forward to the exploration that our users do. Unfortunately, I won't be able to get a chance to ask you all the questions as we're running out of time on the hour. Please put them in the chat, and we can try to come back to them. I'm sorry, please put them in the comments, and we can try to come back to them and answer your questions later. In the meantime, I'd really like to thank you so much, Anton, and thanks again, Atsushi, for sharing your experience with us today. Qiskit Finance and Qiskit Nature will be the subjects of the second part of this two-part series next week. Same time, same place. Signing off for Qiskit Live, I'm Nick Braun, and it's been a pleasure hosting you today. Take care.